On the morning of November 20, 1980, a lake disappeared. Not slowly, not over decades of drought or geological drift. It disappeared in hours. An entire body of water, 1,300 acres of it, drained into the earth so fast that it reversed the flow of a shipping canal, sucked 11 barges to the bottom, and created a temporary waterfall where none had ever existed. The cause was not an earthquake, not a volcanic collapse, not some rare, once-in-a-millennium event that geologists had warned about for years. The cause was a single drill bit, 14 inches wide, attached to a routine oil exploration rig on a quiet lake in southern Louisiana, and a coordinate error so small you could have fit it on a sticky note. What happened at Lake Peigneur was not a flood. It was the opposite of a flood. Two industrial operations, a petroleum drill punching down from above, a salt mine hollowed out from below, had been working inside the same piece of earth for years. Neither company had checked whether their maps agreed. They didn't. When the drill punched through the mine ceiling, the water didn't rise. It fell. And once it started, there was no valve to close, no pump to reverse, no procedure in any manual anywhere in the world that covered what was happening. The physics of the situation had no off switch. 0 lives were lost, not because the safety systems worked, but because the evacuation happened faster than the collapse. The lake didn't drain, it was consumed. Lake Peigneur sat in the Jefferson Island area of southern Louisiana, roughly 10 miles inland from the Gulf of Mexico. It was a shallow lake, averaging only about 11 feet deep across most of its surface. The kind of body of water you'd describe as placid. Unremarkable. A place where local fishermen knew every cove and the herons outnumbered the boats. But underneath that tranquil surface, the geology was anything but simple. The region sits atop a massive salt dome, a geological formation created over millions of years as underground salt deposits, under enormous pressure, slowly push upward through surrounding rock like a column of toothpaste being squeezed from below. These domes are enormous. The one beneath Jefferson Island measured roughly 1 mile in diameter and extended thousands of feet down. Now, salt domes are geologically significant for one specific reason that matters enormously to what came next. They trap hydrocarbons. Oil and gas accumulate along the edges of these domes, pressurized and sealed by impermeable layers of cap rock. For petroleum engineers, a salt dome is a treasure map. By 1980, the Diamond Crystal Salt Company had been mining this dome for over 50 years. The mine beneath Lake Peigneur was fully operational, a cathedral-scale industrial complex of tunnels, chambers, and shafts carved out of solid salt, extending hundreds of feet below the lakebed. Some of those chambers were large enough to fit multi-story buildings inside them, and at the time of the accident, workers were actively down there. Above them, on the surface of the same lake, Texaco had contracted a drilling platform. The target, a petroleum deposit suspected to lie along the flank of the same salt dome. It was a standard exploratory operation. Nothing about the setup, on paper, should have alarmed anyone. That phrase, on paper, is doing an enormous amount of work in this story. Because on paper is where every catastrophic engineering failure looks completely fine. On paper, the coordinates matched the target. On paper, the drill was heading toward oil. On paper, the mine was nowhere near the wellbore. 3 times, on paper. 3 times wrong. The Texaco drilling operation was using a reference coordinate system that placed the target well at a specific position on the lake's surface. But the maps they were working from contained a critical discrepancy. The location they believed they were drilling was not the location they were actually drilling. The drill bit was heading directly toward the mine, and nobody on that platform knew it yet. The bit had been turning for days, nothing unusual. routine vibration data coming back up the drill string, normal rate of penetration. The crew on the platform had no reason to think anything was wrong. What they didn't know was that 12,200 feet below the lake bed, the ceiling of an active salt mine was less than a meter away. The salt dome had been mined aggressively over 5 decades. The tunnels and chambers closest to the surface had been excavated over and over, expanded, connected. The structural geometry of the mine's upper reaches was not a solid block of salt with occasional passages. It was more like Swiss cheese. Interconnected voids, held together by load-bearing pillars of salt that supported the roof. And salt has a property that every geologist knows, but no risk model that day had accounted for at this speed. It dissolves, not slowly, not imperceptibly. Salt dissolves in fresh water at a rate that, in the right conditions, can remove thousands of pounds of material in minutes. Lake Peigneur was a freshwater lake. Its water sat 11 feet deep directly above the mine, and when the Texaco drill bit punched through the mine's ceiling, a hole 14 inches wide, initially, it didn't just create a hole, it created a connection. Fresh water from the lake, under 11 feet of water pressing down from above, roughly the same pressure as a fire hose, began flowing down the borehole and into the mine's upper chamber. The moment that water made contact with the salt walls, it began dissolving them. The dissolution widened the breach. The wider breach allowed more water. More water accelerated the dissolution. The pillars of salt that held up the mine ceiling, the same pillars that had supported the structure for 5 decades, began losing structural mass at a rate nobody had modeled or anticipated. Now here's the thing. There was, technically, a window. In the first minutes after the breach, the hole was still 14 inches wide. A crew, with the right equipment and the right information, might have been able to inject high-density drilling mud into the borehole, a standard blowout control technique, to slow or seal the flow. But the crew didn't know they had breached a mine. They thought the rig was settling. By the time the readings made no sense at all, the hole was no longer 14 inches. It was no longer measurable. The feedback loop had started, and it could not be stopped. The drill platform crew noticed it first as a tilt. The platform, a jack-up rig sitting on legs anchored into the lake bed, began leaning slightly. Not dramatically, just enough to notice. The crew checked the rig, found nothing mechanically wrong, and then noticed something far more disturbing. The water around the platform was moving. In a lake, water doesn't move like that. Not in circles, not toward a center point, not in November with no wind. But it was moving, and it was accelerating. Within minutes, the tilt was no longer subtle. The legs of the rig, designed to sit on firm lakebed sediment, were losing their footing. The floor of the lake was collapsing beneath them, not because of the weight of the rig, but because the mine chambers below the lakebed were failing one by one, creating an expanding void that the lakebed was now sinking into. The evacuation order was given. All 8 crew members on the platform got off. So did the workers in the mine. 50 miners evacuated through tunnels to the surface in a coordinated exit that, in retrospect, was one of the most effective emergency evacuations in industrial history. Every single person made it out. And here is the part of this story that nobody talks about. The evacuation worked perfectly. 50 miners out through tunnels in an industrial emergency, 0 casualties. The logistics of human exit under pressure were flawless. The logistics of the physical system, the maps, the coordinates, the cross-reference, failed completely. We are extraordinarily good at evacuating. We are still learning how to prevent the thing that requires the evacuation. But the platform did not make it out. It tilted, then dropped, then was swallowed by the forming vortex, a whirlpool that had grown from a 14-inch drill hole into a 150-foot-wide aquatic sinkhole in the span of approximately 3 hours. The suction was extraordinary. 11 barges moored nearby were pulled in. Several were later found to have been sucked more than 100 feet below the surface before the pressures equalized, and some popped back up days later. a tugboat went in. Trees along the shoreline were pulled root first into the rotating column of water. The lake, all 3.5 billion gallons of it, drained into the earth. A nearby canal that had previously flowed from the lake toward the Gulf of Mexico reversed its direction entirely as the suction differential overwhelmed the natural flow. For a brief period, the Gulf water rushing in through the reversed canal created a waterfall approximately 150 feet high as it plunged into the now empty lake basin. Think about that for a second. That waterfall didn't exist before. It was engineered by accident. The collapse took roughly 3 hours from the first anomaly to the point where the lake was effectively gone. When the underground pressures finally equalized, when the mine's voids were fully flooded and the suction differential dissipated, the process stopped. What was left was not the same lake. Lake Peigneur had been 11 feet deep at its maximum. In the days following the collapse, divers found that the central basin had been replaced by a crater more than 1,300 feet deep, deeper than any point of the lake had ever been. The inflow of salt water from the Gulf via the reversed canal had fundamentally altered the lake's chemistry. A freshwater lake became a saltwater lake overnight. The entire ecosystem, the fish, the plant species, the bird habitats, was destroyed and replaced by a marine environment. Jefferson Island's Botanical Garden, a renowned horticultural attraction built on the island's salt dome, partially collapsed into the water. The gardens had been there for decades. In hours, significant sections of them were gone. The mine itself, that vast, cathedral-scale industrial complex that had operated safely for over 50 years, was sealed permanently. Those chambers carved into the salt of the dome, those interconnected voids that had housed an entire underground workforce for half a century, are now filled with salt water. They will remain filled for geological time. And then the barges came back. Not all of them, but several. Days after the collapse, as the underground pressures equalized, 9 of the 11 barges that had been sucked to the bottom resurfaced. They floated back up from a crater that hadn't existed a week before into a lake that was now saltwater, in a landscape that was permanently different. They're still there. If you visit Lake Peigneur today, you can see them. Texaco was sued by Diamond Crystal Salt Company, which lost an estimated $1.3 billion in future mining revenue when the mine was permanently flooded. Texaco settled for a figure that was never fully disclosed, but Diamond Crystal received enough to construct a new facility. Several other affected landowners and businesses also received settlements. The drilling operation found no oil. The target reservoir that Texaco had been reaching for, the hydrocarbon deposit that had justified the entire operation, was not there. The exploratory well was a dry hole. The consequences of a drill bit that hit the wrong thing were total. The lake, the mine, the garden, the ecosystem, the geology, all permanently altered, for a well that came back empty. What makes the Lake Peigneur disaster technically singular is not the scale of the failure, it is the mechanism. This was not a structure that was overloaded beyond its design limits. It was not a material that failed under stress it was never meant to handle. It was a coordinate system error, a discrepancy in spatial reference that placed 2 industrial operations in the same 3-dimensional location without either party knowing. That class of failure, what engineers now call a spatial coordination failure, is far more common than the Lake Peigneur outcome suggests. In most cases, these errors are caught before they propagate. A survey mismatch is discovered during permitting. A subsurface scan reveals an unexpected structure. Someone cross-references 2 data sources and notices the discrepancy. At Lake Peigneur, none of those checkpoints worked. The Texaco operation did not use the same spatial reference grid as Diamond Crystal's mine maps. No regulatory body required them to reconcile those references before drilling began. And the dissolving speed of salt, the physical process that turned a 14-inch hole into a 150-foot vortex, was not part of any risk model on that platform. Modern subsurface engineering has absorbed some of this lesson. Today, any drilling operation near an active underground structure, mine, tunnel, aquifer, requires a mandatory spatial cross-reference, submitted and verified before a single bit enters the ground. But the principle embedded in this failure is not confined to drilling. Every city in the world has a version of this problem. Water mains, gas lines, electrical conduits, subway tunnels, parking structures, all sharing the same subsurface volume, all built by different agencies over different decades, all using reference. Systems that were never formally reconciled. The catastrophe at Lake Peigneur required a drill bit. In your city, it might require a construction crew, a backhoe, and an outdated municipal map. The principle doesn't disappear because the medium is different. And here is the detail that the post-incident engineering reports quietly include but never emphasize. The salt dome beneath Lake Peigneur is still there, still enormous, still largely intact. The mine that failed represents a small fraction of the dome's total volume. Nobody has attempted to mine it since. There is a version of November 20, 1980, where the Texaco crew checks their coordinates one more time, where someone prints both reference grids side by side, notices the offset, and redirects the drill. In that version, Lake Peigneur remains a shallow freshwater lake. The salt mine continues operating for decades. The botanical garden grows undisturbed. The fishermen come back in spring. Nothing about that day is remembered by anyone. Instead, the version that happened became a case study in engineering programs, a reference point in subsurface safety regulations, and a permanent alteration of the Louisiana landscape. What the Lake Peigneur disaster teaches is not primarily about incompetence. The engineers involved were not careless people working in a careless system. They were professionals executing a standard operation with the tools and data they had. The failure was invisible to them, not because they weren't looking, but because the systems they were part of did not require them to look in the right place. They drilled into the wrong place. The wrong place turned out to be the ceiling of a 50-year-old underground city. And that city was made of the one material on Earth that disappears the moment fresh water touches it. The salt dissolved because fresh water met salt. The mine collapsed because the pillars lost their mass. The lake drained because the geometry of the voids below it could hold more volume than the lake above. Physics is not negotiable. It doesn't wait for updated maps. And sometimes the most catastrophic engineering failures are not explosions or collapses or fires. Sometimes they are a quiet puncture, a 14-inch hole in the wrong place that sets in motion a chain of events nobody on site had the framework to predict. If the invisible mechanisms behind engineering failures like this fascinate you, consider subscribing. Logistics of Power explores the hidden systems, physical, logistical, geological, that silently govern whether civilizations hold together or fall apart.